slideshow as a Google Slides, but I thought I'd also record it with some of my comments. So basically, we're going to talk about Chapter 18. So some of this is a review. Some of this we're going to add a few new pieces of information, and some of it is just kind of tying everything together. So first of all, I want you to remember what the difference is between climate and weather. So climate is long-term patterns, years, decades, centuries, millennia, right? Weather is day-to-day changes. So make sure you know the difference between those two. And then the other thing to think about is what forces impact our climate. So basically, there's three major ones. The sun, so that's our source of heat, right? The atmosphere, so how that heat gets trapped, and also how the atmosphere, those currents are going to work. And then the ocean currents. So especially remember like our thermohaline circulation heating up Europe, for instance, okay? We're gonna start by focusing on the atmosphere. So we're gonna start talking about greenhouse effect and greenhouse gases. So the greenhouse effect happens when sunlight strikes the Earth's surface and some of it is reflected back towards space as heat. So that's infrared radiation. That then gets re-reflected by the greenhouse gases in the atmosphere. So some of this is natural. The reason we have a livable planet is because our atmosphere has greenhouse gases that help keep our planet warmer than it otherwise would be. But what we're talking about with the greenhouse effect is going to be what we're adding to it. So what has been changing? All right, so if we look at this slide, this is showing basically the greenhouse effect. So here's solar radiation that comes in. Some of it's reflected and some of it's absorbed by the surface. What's absorbed by the surface is then re-emitted as heat, so that's shown by these red lines. And then some of that is then trapped by these greenhouse gases and re-radiated back towards the surface. So this is the overall effect. So it's basically like a big greenhouse, okay? Our key greenhouse gases, and we've talked, I think, about most of these, are carbon dioxide, so mainly from burning fossil fuel, but don't forget about these two effects. So cellular respiration and photosynthesis are going to affect overall CO2 levels. So when we deforest, we decrease photosynthesis, we increase levels in the atmosphere. So think about that, make sure that makes sense. Methane, so methane can come from landfills, cattle and sheep, remember they burp out methane, natural gas leaks, things like rice cultivation, nitrous oxide, also from fossil fuels, from fertilizer use, livestock waste, and plastic manufacturing. Our fluorinated gases, so what else do these contribute to? Remember our ozone hole, but these are also greenhouse gases, and these come from things like air conditioners, refrigerators, foam, insulation. And then down here is others. Water vapor is also a greenhouse gas, but we usually don't talk about that when we're talking about the greenhouse effect because water vapor is going to be a constant. All right, so this is kind of a natural amount, so we're not affecting this as much as we are affecting these other ones. All right, and then this is showing the relative heat trapping abilities of a few of these. So they're not all created equal. And so these numbers are in CO2 equivalents. So what this means is that the relative heat trapping ability of methane is 23 times that of CO2. So if we just look at this, we think, oh, well, nitrous oxide should be much more of a concern than carbon dioxide. But, you know, we always talk about carbon dioxide. And that's because there's so much of this that this is the most prevalent one. And so this really is the most important greenhouse gas. It also is a little bit more persistent in the atmosphere than these gases. So that helps even off these numbers as well. All right, and you can see if we look here at these graphs that all three of these major greenhouse gases have been increasing since the beginning of the Industrial Revolution. All right, so again, we're going to focus on this carbon dioxide and why this is increasing. And this hint about the carbon cycle, that's again, don't forget how photosynthesis, respiration, how natural things affect the carbon cycle. All right, and so here, if we look at, this is actually dividing up carbon dioxide and how it's moving into and out of the atmosphere. The green arrows are natural fluxes. So we've got photosynthesis, taking in carbon dioxide, respiration, releasing it. Okay, same thing in the oceans. You have the oceans absorbing it and releasing it. Okay, the red arrows now are the human caused or the anthropogenic fluxes. And so if we take all of these together, notice the net accumulation is we're adding CO2 to the atmosphere. All right, some other things we need to think of. So here is showing the total radiative forcing of various things that can affect the atmosphere. So here's our carbon dioxide. So obviously that's increasing heat in the atmosphere. All right. Here are our methane, nitrous oxide, halocarbons, right? Also increasing heat. Ozone, it depends where it is. So remember, tropospheric is the bad ozone. Stratospheric is the good ozone. So that actually traps some of that UV radiation that's incoming. So that has a slightly cooling effect. All right. Surface albedo. So we didn't talk about this, but albedo is the capacity to reflect light. So darker surfaces have less albedo. So think about glaciers. They're snow covered, right? Ice. So they reflect light from the sun. Light surfaces are going to take up less heat. So they're going to have more albedo. But as we're increasing temperature, those ice caps are starting to melt. So more land is now visible. So we're decreasing the albedo. And also things like soot on snow is going to contribute to warming. So this surface albedo has both effects. Aerosols, we said cool, and then cloud albedo. So they also reflect incoming radiation, are cooling. So what we want to know is what, again, is the net of all of these different things. And if you look down here, the summary is 2.3 watts per meter squared of cumulative radiative forcing. Again, we're heating the atmosphere. Okay. If you remember from that clip we showed in class, there are other influences on climate. So these are the Milankovitch cycles, solar output. The ocean actually can absorb a lot of carbon, but it absorbs it more slowly than we're adding to it. And then the ocean circulation. So remember, things like Northern Europe is warmer than we would expect because of this ocean circulation. So these things all are other influences on climate. So how do we study climate change? So many of you talked about these as we went through the different graphs, but so just keep in mind three things. When we're talking about the past, we're talking about proxy indicators. These are stand-ins. We can't take direct measurements anymore. So we have to find ways that we can figure out what happened in the past. And some of the main ways are ice cores. So remember that picture showing the little bubbles in the ice that show air that's been trapped thousands of years ago, and we can measure the CO2 in that. Cores from sediment at the bottom of the ocean. Tree rings. So when tree rings show how well a tree grew in a certain year, that can tell you something about the climate at that time. And data from coral reefs. So coral reefs also grow over time. So it's very similar to this tree ring growth rate. Okay. For the here and now, we have direct measurements that tell us about the present. So we can measure temperature, we can measure the chemistry of the atmosphere and the oceans, and we can measure precipitation rates. And then finally, in the future, we have to come up with models. So these are supercomputers, right, that can take thousands of points of data and then model how this will impact the future. And then what people do is they see, well, here's what's happening now. Does the model fit that? And then if it fits that, we can be more confident that it's going to predict the future. Slide to show, because it really shows all the different effects and it lists them out. So here's biological trends and effects, social trends and impacts. Okay, so you really should have a good understanding of all of these different impacts and what they're affecting. So is it the environmental? Is it human? Is it economic? How are these all fitting together? Okay. All right. So we're just going to go through a few of them. So mountaintop glaciers are receding. Here's a picture from Grinnell Glacier in 1938. And here is the same glacier in 2005. So this is in Montana. Look at the difference in the snow cover. And this graph shows decreasing glaciers just in the last, 20, 25 years. And then the impacts, sudden floods, reducing summertime water supplies, reducing snow cover at high latitude. All right. We also can see that sea levels have risen since 1870. So again, here's our proxy indicators, and we can see that we're not quite sure. So here's our area that we're not quite sure of, and that gets less as we get closer to the present. The red is sort of present day, what we have direct measurements for. So you can see that the sea level is rising. And here are the three main reasons. So thermal expansion, as water gets warmer, it becomes less dense, so it takes up more space. And then melting on any of these glaciers, ice caps, Greenland, and Antarctic ice sheets. So remember, things that are on land, if they melt and release water, that's going to increase the sea level rise. And some of the impacts are probably pretty obvious. So beach erosion, coastal flooding, saltwater intrusion into aquifers. So remember how the aquifers, go back to that picture, they eventually do have a connection to the ocean. So as saltwater rises, they actually can force the freshwater back in aquifers. And so more people are having saltwater come up into their aquifers. This is really an issue in southern Florida, especially. So for the U.S., 53% of the population lives in coastal areas. And obviously, any of those island nations are going to be really concerned about this. All right, here's showing some of the places in the U.S. that are affected. So blue, darker colors, more effects. Here's New York City, right? So they're spending billions of dollars to recover from Superstorm Sandy and future flooding, all right? Washington, D.C. is actually pretty low level. A lot of those monuments are vulnerable to flooding. Norfolk, Virginia. So one of the interesting things here is this is one of our major naval bases. So even though the official government policy is that global warming isn't happening, the military needs to plan for it because they need to figure out what's going to happen to some of their naval bases. Here's Florida. So this is not mentioning it, but especially southern Florida, so Miami Beach, Miami area, really has to deal with current flooding now. And they're trying to figure out what to do about that. New Orleans is actually below sea level, right? And then the same thing happens on the West Coast. All right, so Miami Beach, as I said, is one of those areas that is seeing increased flooding now, and they actually see dry day flooding. So on perfectly sunny days, all of a sudden water just starts rising up and covering the streets. So they've been doing things like rising the streets up, so building the streets higher and installing a lot of pumps to try to pump the water out. So this is a temporary adaptation. If sea levels keep rising, Miami, though, is in trouble. All right, so that's sea level rise, right? Heat waves, we have also heard about how those are expected to increase. So remember, we had the graph that showed the increase in heat waves in Europe, so in France and Greece. But here's basically what's expected, some different models showing heat index in July over the next century. And here's the overall rise in summer mortality rates that are attributed to hot weather episodes. So you can see they've already risen, and the expected rate is going to be much higher. Impact on forests. So remember when we were talking about biomes, right? Which forests are in what areas are dependent upon temperature and precipitation. So as those change, our forests are going to change. So here's kind of the current distribution. So here we are in the green area. So this is oak, hickory, oak pine forest. And then slightly north of us, we have this maple, beech, birch forest. But look down here at what's predicted is these forests are going to spread northward as the temperature rises, and these maple, beech, birch are then going to also spread northward and basically leave the U.S. So our forests are going to change, right? We also have animals. So birds are moving north. So the center of purple finch's winter range has shifted. Some birds are choosing not to migrate anymore because as weather stays warm enough where they are and there's urban areas that sometimes provide food, they don't move anymore. They're also forcing animals upslope. So remember, as we go up in elevation, we also get cooler. So some animals' ranges have moved up the mountain, all right, which is a problem as you get to the top, right? One of the other major impacts that people are only just beginning to realize maybe in the last 10, 20 years is ocean acidification, all right? So CO2 in the atmosphere can actually be absorbed by the ocean. So CO2 in water forms carbonic acid. All right, for those of you that loved chemistry, notice this is diprotic. There's 2 hydrogens. So it can lose the first one. So here's our hydrogen increase, and it releases bicarbonate ions, right? This bicarbonate ion can then release another hydrogen ion and carbonate ions. All right, so this is normally what we call the bicarbonate buffer system in the ocean, and this maintains the pH historically at about 8.1. All right, and that's what all life in the oceans have basically evolved to live in. As we're now increasing the amount of CO2, we're increasing the input here. So remember, that's going to drive our equations to the right. So we're increasing our acid levels, so the pH decreases slightly. And we also, as we get more hydrogen ions, we force this equation back to this equation. So we're also decreasing the amount of available carbonate, all right? This is important because a lot of marine organisms have shells that are made of calcium carbonate. So if we remove the available carbonate, they're going to have a much harder time making their shells. So this affects things like oysters and clams and corals and sea urchins. So those are all very important either bases of the food chain. We talked about how corals are creating environment where there's high biodiversity. So what's going to happen as those things decrease? All right, and this image is basically just showing the summary of all that. So here's what we're doing. We're creating more bicarbonate and less carbonate, so less shells. And people have actually done research and found that these organisms are having a much more difficult time making shells. Okay, if you're interested in more information, there's a little video that's linked in the slideshow, and this is an article that's linked. All right, the other thing that climate change is doing is it's affecting humanitarian, geopolitical, and national security. So if you live in a country where you're being impacted by increased droughts, increased heat, right, less things are growing, you're going to try to move somewhere else. So this impacts migration patterns. People are then going to fight over available resources. So it might increase conflicts. So this is also a national security problem. All right, again, here's another one of those tables. Go over this carefully. Some predicted impacts of climate change. Try to group them. Which ones are environmental? Which ones are economic? Which ones, impact agriculture? This is a great one to know. These things often come up on free response questions. All right, so how do we respond to climate change? 2 major ways: mitigation. So figuring out how to reduce greenhouse gases. So can we decrease the rate at which we're increasing? And adaptation. We accept that there's impacts. What can we do to make those impacts less? So adaptation is things like build seawalls, reduce coastal development, adjust farming practices. So maybe more drought-resistant crops, modify water management. All right. So here are some specifics, particularly for the mitigation part. So how do we reduce climate change? So agriculture good land practices. So the soil actually stores a lot of carbon in root systems, in biological biomass that gets saved in the soil. Good agriculture practices help increase that. Buildings, more insulation, right? Energy Star, appliances and building practices, subsidies for solar and other types of energy that don't emit carbon dioxide. Our energy supply, we actually subsidize fossil fuel right now. So fossil fuel is cheaper than it otherwise would be. So if we reduce fossil fuel subsidies and make it more expensive, it would encourage people to switch. All right, we can also do things like a carbon tax, which I'll talk about in the next slide. International treaties. So how do governments figure out how, as an entire globe, we're going to deal with this problem? This is not something that just affects one country. This is kind of a tragedy of the commons writ large, right? Industry, penalties for carbon emissions, transport, CAFE standards. Do you know what CAFE standards are? Those are the standards that tell car manufacturers what overall miles per gallon all of their cars sort of must meet if you group them all together. These were raised under the Obama administration, but the Trump administration has rolled some of that back. And subsidies for public transportation. So encouraging people to use rail and light rail options, which, remember from when we talked about urban planning, these are much cheaper and more energy efficient alternatives. And waste management. So remember that landfills generate methane. So we can actually require methane capture on some landfills. All right, I just wanted to say a little bit more about carbon pricing. So this is the idea that we're going to compensate the public for external cost. All right, so remember what external costs are. I think that was chapter 2. So we want to compensate the public for that from fossil fuel emissions and climate change. And there's 2 main ways to do that: carbon trading and carbon taxation. So carbon trading is basically when the government sets up a market in permits for the emission of pollutants. All right, and then these permits can be traded between different, let's say, industrial plants. And this is usually set up as a cap and trade system. So the government sets a cap on the amount of pollution it allows, and then the emitters can trade these permits back and forth depending on how their particular plant is doing. Okay. Currently, California has a cap and trade program that seems to be working. Other countries have tried it. So the European Union tried this, but they set the initial cap too high. So it didn't wind up working as a good system to reduce pollution. All right. The other way to influence carbon pricing is to tax it. So this is a type of green tax. And the problem with this is people argue that it might cause the polluters to pass the cost to consumers, and consumers never want to hear that. So one of the approaches to this is to use a fee and dividend approach and to try to make this a revenue neutral carbon tax. So in other words, what happens is the government receives funds from polluters and then transfers it back to people as a tax refund. All right, so this is just a little bit more about cap and trade that kind of explains it. So first of all, the government establishes a cap. So here's current emissions, and it's going to say, nope, we want the current emissions down here. So right now, both of these plants are exceeding their emissions. All right, but plant A, they do a good job in cutting emissions, so they get below the cap. Plant B fails to cut emissions. So now plant B is going to buy permits, those allowances from plant A. So A will make some money off of this. So that motivates them to do this. And plant B then is under their total because they've bought some of these extra permits. So as long as you have this set at a reasonable level, this should over time reduce the amount of carbon dioxide. And the thought is that over time, as companies get successful at this, you keep lowering the overall cap. All right, here is showing what some of the international movement on this has been. All right, so The first really big one was the Kyoto Protocols. So this was the late 1990s. This was agreed upon ways to try to limit carbon dioxide use. The United States was the only developed country that did not ratify the Kyoto Protocols. The next big one was in Copenhagen, but this was really kind of in disagree. So nations agreed to a 2 degree Celsius increase, but they really couldn't figure out how to do it. And so there was a lot of arguing. Around this time, a little before this, notice the IPCC and Al Gore win a Nobel Peace Prize. So Al Gore really sort of lobbied kind of tirelessly for this. And this is around the time that An Inconvenient Truth came out. So if you haven't seen that, it's a little dated right now, but it's still a good film. And in the last few years, there's been a sequel. And the sequel talks about what happened in this Paris conference in 2015, and basically how the nations were able to sort of pull together and pledge emissions cuts. Initially, this happened during the Obama administration, and the Obama administration signed on to the Paris Agreement, but Trump pulled us out in 2017. All right. Even with these agreements, though, let's look at what's happening. So business as usual, we would expect to see a 4.5 degree increase. Paris commitments lower that a little bit to 3.5 degrees. But here's our goal down here, and that's still saying it's going to increase 2 degrees. So even under the best case scenarios, we're not getting back to what it was, or we're not going to stop global warming right now. It's just going to warm at a slower pace. So there are people that are sort of thinking in larger terms. Instead of just reducing the amount we emit, can we figure out ways to actually pull carbon out of the atmosphere? All right. Some of these ways are natural. Let's plant more forests, right? Increase photosynthesis. We increase how much CO2 comes out of the atmosphere. All right. But people are also thinking about, well, what are some sort of man-made things we can do? So this falls under carbon capture and sequestration. So the idea is figure out, capture carbon dioxide from the air, transport it somewhere where it can then be injected down deep in the earth into an injection well, and let's store it there. So notice this is deep enough to be underneath, let's say, drinking water aquifers, or any water that we might be tapping into. So we're going to inject it deep under this impermeable seal. All right, and there are companies that are experimenting with this. There are some sort of trial experiments going on. And there are a whole bunch of other ideas people have come up with. So these fall under the category of geoengineering. So we're going to try to figure out, okay, what could we do to cool the climate? All right, so there have been a variety of ideas, some crazier than others. So you could put mirrors in orbit to reflect solar radiation. All right, remember we said those sulfate aerosols, like from a volcano, can cool the climate. Well, what if we injected sulfate aerosols into the stratosphere? Would that work to cool the climate? All right, here again, here's restore forest. So this is kind of a natural way to do it. We could seed clouds with seawater mist, right? We could erect land-based mirrors. Here's a big one that comes up every once in a while. We could actually fertilize the ocean with iron. So remember, iron's when there's micronutrients. So it's usually limiting factor in growth. So if we add more, we're going to increase those plankton blooms. Remember, plankton, the phytoplankton, photosynthesize. So if we increase the amount they photosynthesize, they take in more carbon from the atmosphere. They eventually die, sink to the bottom of the ocean, and that carbon is now trapped in sediments. Right? This is what happened. When we think of fossil fuels, it was originally growth of plants that got trapped in sediment over millennia. So you could probably think of reasons why we should be very cautious with all of these plans, right? We don't really know what's going to happen, and we don't want to do something that could screw up the whole globe, right? So we don't want to overcool, right? What happens here when we fertilize the ocean? We don't really know. There have been some studies done that this kind of is only temporary, so it probably won't do what people want it to do. But these are some ideas under engineering. Okay, I think we're getting towards the end. Here is another one of those big slides. If you get this slide, you get this chapter. So you might want to try to recreate it, but look at what we have here. Here's our greenhouse gas emissions, right? 2 causes, fossil fuel use, deforestation. Both of those impacted by population growth and growth in consumption, right? We get more greenhouse gases, it warms the atmosphere. Warming the atmosphere increases temperature in the air, the ocean, and alters precipitation. Each of those things then has consequences, which hopefully you've learned something about. Then those even have more consequences. And here's where we feel it eventually, even in human society. All right. As you think about all these, think about all the solutions we've talked about. How can we decrease this? How can we decrease this? Right? What are some ways we can adapt to some of these things? Right? So come up with solutions and you can maybe add them into your concept chart.